Hello there. Welcome to the Science Owl Station channel. Today we journey toward a world so vast, so quietly powerful, that it outweighs all its planetary siblings combined. A silent giant drifting in the dark, known to ancient skywatchers as a king among wandering stars. Right now, as you listen, Jupiter is there, far beyond the faint rust glow of Mars, beyond the scattered stones of the asteroid belt, turning slowly against the velvet black of space. Through a modest backyard telescope, it appears as a bright, steady lantern in the night sky, its light calm and unwavering. If you happen to know where it is this evening, perhaps glance upward later. And before we drift deeper, tell me in the comments where in the world you are listening from, and what time it is there. Is it late at night? Early morning? Let's share this quiet moment across continents. Long before spacecraft and spectrometers, the ancient Romans looked up and saw a brilliant object that moved differently from the fixed stars. They named it after their supreme god Jupiter, the ruler of thunder and sky. In Greek tradition, this same celestial authority was known as Zeus. Feels fitting, doesn't it, that the largest planet in our solar system would carry the name of a king of gods? Even with the naked eye, Jupiter's presence is dignified. It does not twinkle like distant stars. It shines steadily because it is close enough, cosmically speaking, that its light does not flicker through Earth's atmosphere in quite the same way. That steady glow made ancient observers pay attention. They tracked its slow march across the constellations. They wove myths around it, and without realizing it, they were watching a planetary giant whose gravity would shape the destiny of the entire solar system. Jupiter is often described as Earth's quiet guardian. This is not poetic exaggeration. With its enormous mass, it exerts a profound gravitational influence on wandering comets and asteroids. Many icy bodies from the distant outer solar system, nudged inward by subtle gravitational tugs, find their paths altered when they pass near Jupiter. Some are captured. Some are flung outward again into deep space. Some are pulled into collision with Jupiter itself. In this way, the giant planet acts as both shield and sculptor, redirecting cosmic debris that might otherwise travel deeper toward the inner worlds. Its size is difficult to comprehend in ordinary terms. Jupiter's equatorial diameter is more than 11 times that of Earth, about 11.2 Earths laid side by side across its face. If Earth were a small grape, Jupiter would be closer to the size of a grapefruit resting beside it. And yet, even that comparison feels inadequate because Jupiter's volume is so immense that more than 1,300 Earths could fit inside it. Mass tells an even deeper story. Jupiter contains 318 times the mass of our planet. In fact, it is more than 2.5 times as massive as all the other planets in the solar system combined. Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune. Gather them together in your imagination, add up all their substance, and Jupiter still outweighs them. This extraordinary mass is what grants Jupiter its protective reputation. Gravity scales with mass. The heavier an object, the more powerfully it bends the paths of nearby bodies. Jupiter's gravitational well is deep and wide, extending far into space. Objects that drift too close feel that pull immediately. Some are drawn into orbit around the giant. Others accelerate and change direction dramatically, like pebbles slung from a cosmic sling. Yet for all its dominance, Jupiter is not aggressive. It does not chase. It does not hunt. It simply exists, immense, patient, steady, allowing the natural laws of motion and gravity to play out around it. Over billions of years, that quiet presence has influenced the architecture of our planetary neighborhood, the spacing of planets, the stability of orbits. Even the survival of Earth itself may owe something to this distant giant. When early astronomers turned telescopes toward Jupiter in the 17th century, they discovered something astonishing. Tiny points of light lined up beside it, shifting positions night after night. Those points were moons, worlds of their own, circling Jupiter just as our moon circles Earth. Suddenly, it became clear that not everything in the heavens revolved around our planet. Jupiter helped reshape humanity's understanding of its place in the cosmos. And still, even now, Jupiter continues to teach us. Modern spacecraft have approached it, orbited it, tasted its radiation belts, and peered through its swirling cloud tops. But from Earth, to the unaided eye, it remains that same calm beacon the Romans once named for their sky god. If you are enjoying this gentle exploration, consider subscribing or leaving a quiet like. It helps the channel grow, and it lets me know that you enjoy drifting through these vast subjects together. As we settle into this journey, imagine Jupiter suspended in darkness. Its upper clouds form soft bands of cream, rust, and gold. Beneath those clouds lies a depth so vast that it defies everyday intuition. Around it, dozens of moons trace silent arcs. Beyond it, the cold outer reaches of the solar system extend into shadow. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. And as Jupiter turns in the distance, massive yet serene, we begin to notice something else about it. Something subtle, something dynamic, the way it spins. If we could hover above Jupiter's cloud tops, held safely in imagination, untouched by its crushing gravity, we would notice something remarkable almost immediately. The planet is not still. It is not slow. It is turning with astonishing speed, completing one full rotation in just under 10 hours, about 9 hours and 55 minutes, to be more precise. That means that while Earth takes a full 24 hours to turn once on its axis, Jupiter spins more than twice as fast, despite being more than 11 times wider. The scale of this motion is difficult to hold in the mind. Its equator stretches roughly 440,000 kilometers around, and yet, in less than half of an Earth day, that immense circumference sweeps once through space. Imagine standing, if standing were possible, at Jupiter's equator. You would be carried along at tens of thousands of kilometers per hour. Of course, there is no solid ground there, no quiet stone beneath your feet, only layered clouds and deeper currents of gas. But the motion would be undeniable. This rapid spin has consequences. It reshapes the very body of the planet. Because of centrifugal force, Jupiter bulges outward at its equator. Its equatorial radius is about 7% larger than its polar radius. In simpler terms, Jupiter is slightly flattened, wider around the middle, gently compressed at the top and bottom. From a distance, this flattening is subtle, but it tells a story about balance, about gravity pulling inward while rotation presses outward. Jupiter lives in the tension between these forces. Gravity, immense and patient, gathers the planet's mass toward its center. Rotation, swift and persistent, urges the equatorial regions outward. The result is a giant sphere that is not quite a sphere, but something softer, slightly stretched. This fast rotation also organizes Jupiter's atmosphere into bands, long, parallel stripes that wrap around the planet. These bands are visible even through small telescopes from Earth. Pale zones and darker belts alternate across the globe, like ribbons wound around a spinning lantern. Within these bands, powerful jet streams race in opposite directions. Some flow eastward, others westward. The boundaries between them are places of turbulence and subtle friction. Yet because Jupiter spins so quickly, these currents are neatly arranged into layers, each moving with its own rhythm. On Earth, weather systems form and dissolve across continents and oceans. Storms swirl, then fade. Winds shift unpredictably. But on Jupiter, the rapid rotation stabilizes these atmospheric lanes. It gives structure to chaos. It stretches storms into elongated shapes and keeps them aligned along latitudes. Even the planet's magnetic field, so powerful and vast, feels the influence of this rotation. Deep within Jupiter, electrically conducting material churns and flows. The speed of the planet's spin helps generate enormous electrical currents, amplifying its magnetic presence. The turning of Jupiter is not merely surface motion. It is woven into the behavior of its entire interior. If we pause for a moment and think gently about that, this enormous world turning so swiftly in silence, it becomes almost meditative. A colossal sphere of gas, hundreds of thousands of kilometers across, rotating faster than any other planet in our solar system. Mercury spins slowly. Venus turns in a languid, retrograde drift. Even Saturn, elegant with its rings, takes over 10 hours. But Jupiter is the fastest of them all. Why does it spin so quickly? The answer lies far back in time, in the early formation of the solar system. When Jupiter was gathering material from the primordial disk of gas and dust, it accumulated angular momentum, tiny rotational motions from countless particles adding together. As the growing planet contracted under gravity, it spun faster, much like an ice skater drawing in their arms during a spin. Over billions of years, that speed has barely diminished. In the vacuum of space, there is little to slow a planet's rotation. No thick atmosphere of another body pressing against it. No ocean tides large enough to meaningfully break its motion. So Jupiter continues to turn, steady and rapid, as it has for eons. Its swift day also means that sunrise and sunset, if we could define such things within clouds, would come quickly. Light from the distant sun sweeps across its atmosphere in less than 5 Earth hours. Shadows shift swiftly across the tops of storms. The planet's cloudscape is never static. It is always being carried forward by rotation. And yet, despite this speed, there is no sense of urgency in Jupiter's existence. It does not rush. It does not strain. It simply rotates, again and again, in a rhythm that has become part of its identity. As we drift beside it in imagination, we can almost feel that motion, not as turbulence but as continuity, a smooth, unbroken turning, the soft repetition of day and night across a world without solid ground. Earlier, we spoke of Jupiter as a guardian. Its mass protects. Now we see another dimension of its nature, its motion, massive yet swift, enormous yet dynamically alive. And within those rotating cloud bands, something else endures. A storm older than modern civilization. A vast crimson oval that has watched centuries pass beneath it. We will turn our attention there next, to a feature so iconic that even small telescopes reveal its presence. A storm that refuses to fade. As Jupiter continues its swift and silent turning, our gaze settles upon one of the most enduring features in the entire solar system, a vast, rust-colored oval embedded within its southern hemisphere. It is known simply as the Great Red Spot. Through a small telescope, it appears as a soft blush against cream-colored clouds. Through larger instruments, it reveals swirling textures, layered eddies, and a boundary that curls inward like a slow, atmospheric whirlpool. This storm has been observed continuously for at least 3 centuries. Some historical records suggest it may have been seen as early as the 1600s. That means it has been churning since before the invention of the steam engine, before electricity illuminated cities, before humans first imagined flight. The Great Red Spot is not a solid feature. It is not a mark painted onto Jupiter's surface, because Jupiter has no solid surface. It is a storm, a vast, high-pressure anticyclonic system rotating counterclockwise in the planet's southern hemisphere. Winds along its edges can exceed 400 kilometers per hour. And yet, despite that velocity, the storm's overall demeanor feels strangely steady, almost patient. At its widest measured extent in the late 19th century, the Great Red Spot stretched approximately 25,000 kilometers across, large enough to swallow more than one Earth side by side. In recent decades, it has gradually shrunk. Today, it measures closer to 16,000 kilometers in width. Still enormous, still capable of engulfing our entire planet, but quietly diminishing over time. Why it has endured so long remains a subject of careful study. On Earth, storms dissipate when they lose access to warm ocean waters or when they encounter land. They weaken as friction disrupts their circulation. But on Jupiter, there is no land to interrupt a storm's rotation. No mountains, no continents, only deep layers of gas feeding energy upward from below. Jupiter radiates more heat than it receives from the sun. That internal warmth rises slowly through the atmosphere, fueling convection. The Great Red Spot draws upon this energy, sustained by the planet's own slow gravitational contraction. It also feeds on the surrounding jet streams, those powerful east-west currents we discussed earlier. The storm sits between 2 opposing atmospheric bands, which may help stabilize and confine it. If we could hover just above its cloud tops, we would see towering structures within the storm, clouds rising perhaps dozens of kilometers higher than surrounding layers. Lightning has been detected in Jupiter's atmosphere, flickering in deeper regions. The Great Red Spot likely contains complex vertical motions, air rising at the center, descending at the edges, cycling endlessly. Its color remains another quiet mystery. The reddish hue may result from complex chemical reactions triggered by ultraviolet sunlight interacting with compounds such as ammonia, methane, and trace elements. Over time, these reactions produce chromophores, molecules that absorb certain wavelengths of light, leaving behind the soft red tones we observe. But the precise chemistry is still debated, and so the storm endures. It rotates once roughly every 6 Earth days, around and around like a patient clock marking centuries instead of hours. Interestingly, Smaller storms have occasionally merged with the Great Red Spot. In the early 21st century, astronomers observed tiny vortices drifting close, sometimes being absorbed, sometimes torn apart. These interactions may influence its size and strength. Yet even as it shrinks slowly over decades, it refuses to disappear. There is something almost meditative about imagining this storm, a system of wind and cloud older than modern history, spinning on a planet so vast that human timescales feel brief by comparison. While empires rise and fall on Earth, Jupiter's crimson oval continues its steady rotation. It is not alone in Jupiter's atmosphere. White ovals, brown barges, and transient storms appear and fade within the banded cloudscape, but none match the scale or longevity of this feature. It has become emblematic of Jupiter itself, a signature, a visible reminder of the planet's dynamic nature. When spacecraft pass near Jupiter, they capture images of the Great Red Spot in exquisite detail. Filaments curl along its edges. Smaller eddies spin within it like nested spirals. The storm is not uniform. It is layered and textured, alive with subtle motion. And yet, from Earth, it remains a quiet oval glimpsed across hundreds of millions of kilometers, a subtle stain in the clouds of a giant world. Earlier, we reflected on Jupiter's size and its rapid rotation. Now we see how those qualities combine: mass providing energy, rotation organizing flow, to create something persistent. A storm that defies ordinary expectations. But for all its power, Jupiter itself once occupied a more ambiguous category in human imagination. Composed mostly of hydrogen and helium, it resembles a star in material, yet it never ignited. It hovers in a delicate boundary between what might have been and what is. And so, as the Great Red Spot turns slowly beneath the sunlight, we begin to consider another question: what separates a giant planet from a small star? As we drift away from the swirling crimson of the Great Red Spot, a quieter thought begins to form, one that has followed Jupiter for decades in scientific conversation. What if this enormous planet had become something more? What if, under slightly different circumstances, it had ignited and begun to shine? Jupiter is composed primarily of hydrogen and helium, the very same elements that make up our Sun, roughly 90% hydrogen, about 10% helium, with only trace amounts of heavier elements mixed within. In composition, it resembles a star more than it resembles Earth or Mars. It is, in a sense, a fragment of stellar material that never quite crossed a crucial threshold. Because of this, Jupiter is sometimes called a failed star. The phrase sounds dramatic, but it is not meant as criticism. It simply reflects physics. For a star to be born, gravity must compress hydrogen gas so intensely that temperatures and pressures at the core become high enough to trigger nuclear fusion. Fusion is the process by which hydrogen nuclei combine to form helium, releasing vast amounts of energy. It is the engine that powers every star in the universe. Jupiter, immense as it is, does not have enough mass to ignite this process. To begin sustained hydrogen fusion, an object would need roughly 80 times Jupiter's current mass. 80 Jupiters combined into one would create pressure sufficient to light that internal fire. Below that threshold, gravity cannot squeeze the core tightly enough. The temperature rises, yes, but not to the millions of degrees required for stable fusion. There is an intermediate category between planet and star known as a brown dwarf. Brown dwarfs are sometimes called failed stars as well, though more accurately they are substellar objects. They can fuse deuterium, a heavier isotope of hydrogen, for a short time. To qualify as a brown dwarf, an object needs about 13 times Jupiter's mass. Jupiter itself falls well below even that mark. It remains firmly planetary, yet it is interesting to imagine. In the earliest days of the solar system, as gas and dust circled the young sun, Jupiter began forming quickly. It gathered material with astonishing efficiency. Some models suggest that had the protoplanetary disk contained just a bit more mass, or had Jupiter formed slightly earlier, it might have accumulated far more material. But it did not. Instead, Jupiter grew large enough to dominate its region, to sculpt the architecture of the solar system, but not large enough to compete with the Sun. It occupies a delicate balance, massive but not luminous, powerful but not radiant. If Jupiter had become a star, our solar system would look profoundly different. We might orbit a binary system, two stars circling each other. The gravitational dynamics would be complex. The inner planet's orbits might be unstable. Earth's climate might never have allowed life to flourish. In a quiet way, Jupiter's restraint, its failure to ignite, helped preserve the calm conditions necessary for our existence. There is another subtlety here. Even though Jupiter does not fuse hydrogen, it does produce heat. As it slowly contracts under its own gravity, potential energy is converted into thermal energy. This process, known as Kelvin-Helmholtz contraction, allows Jupiter to radiate about 2.5 times more energy than it receives from the Sun. So while it is not a star, it is not cold and inert either. Deep inside, heat lingers from its formation and from its gradual compression. That warmth rises slowly through layers of hydrogen and helium, feeding storms and jet streams above. When we look at Jupiter through a telescope, we see reflected sunlight, soft bands, and gentle hues. But beneath those clouds lies stored heat from billions of years ago. A quiet internal glow, not bright enough to shine independently, yet persistent. The phrase failed star can sound dismissive, but perhaps it is better to think of Jupiter as something unique, a bridge between categories. Too large to resemble rocky planets, too small to ignite like a star, a giant gas world suspended in cosmic equilibrium. In the vastness of the universe, there are objects far more massive than Jupiter, true stars blazing with fusion. There are also countless smaller planets drifting quietly around distant suns. Jupiter sits between extremes, reminding us that nature does not divide reality into sharp boundaries. Instead, there are gradients, thresholds, gentle transitions from one state to another. And so Jupiter remains what it has always been, a gas giant, luminous only by reflection, massive yet unlit. As we imagine its deep interior, compressed by gravity, warmed by slow contraction, we begin to wonder what lies beneath those clouds. If it is mostly hydrogen and helium, what happens to those elements under such extraordinary pressure? How do they behave when squeezed far beyond anything we experience on Earth? The answer takes us deeper, far below the visible cloud tops, into layers where hydrogen itself begins to change its character. If we could descend gently through Jupiter's upper clouds, floating downward as though carried by a slow and patient current, we would first pass through layers of ammonia ice crystals, pale and softly luminous in reflected sunlight. Below them, deeper clouds composed of ammonium hydrosulfide drift in muted browns. Beneath those, water clouds form in thicker, darker bands. Each layer marks a subtle change in temperature and pressure, a quiet transition from the visible atmosphere into the planet's immense interior. Unlike Earth, there is no sudden boundary where sky becomes ground. No solid surface waits below. Instead, the gas simply grows denser, heavier, more compressed, until the distinction between atmosphere and interior gradually disappears. As we move further downward in imagination, pressure increases steadily. On Earth, pressure rises modestly as we descend beneath the ocean's surface. On Jupiter, the increase is far more dramatic. The weight of hundreds of thousands of kilometers of gas presses inward relentlessly. Hydrogen, the simplest and most abundant element in the universe, begins to behave in unfamiliar ways. Near the outer layers, hydrogen exists as a gas molecules composed of two hydrogen atoms bound together. But as pressure intensifies, these molecules are squeezed closer and closer. The gas transitions into a liquid state, not because it is cold, but because it is compressed. The distinction between gas and liquid becomes blurred under such extreme conditions. Deeper still, something even more remarkable occurs. The pressure becomes so immense that hydrogen molecules break apart. Electrons, once bound to individual atoms, begin to move freely. The hydrogen transforms into what scientists call metallic hydrogen. Metallic hydrogen does not resemble metal in the way we typically imagine. There is no silver sheen, no solid surface to touch. Yet electrically, it behaves like a metal. It conducts electricity with extraordinary efficiency. It responds to magnetic forces. It flows like a liquid, yet carries electric currents within it. This layer of metallic hydrogen is believed to occupy a vast region inside Jupiter, perhaps extending tens of thousands of kilometers deep. It is here, in this immense ocean of conductive fluid, that Jupiter's powerful magnetic field is born. As Jupiter rotates so rapidly, this metallic hydrogen churns and circulates. The movement of electrically conductive material within a rotating body generates magnetic fields through a process known as the dynamo effect. On Earth, our magnetic field arises from the motion of molten iron in our outer core. On Jupiter, the scale is far greater. Instead of iron, it is metallic hydrogen, flowing, convecting, spinning in alignment with the planet's swift rotation. The result is a magnetic field of extraordinary strength. But we will linger on that in more detail soon. For now, it is enough to imagine this transformation. A simple element, hydrogen, the same hydrogen that fuels stars, compressed into a state rarely seen anywhere else. In laboratories on Earth, scientists have attempted to create metallic hydrogen under extreme pressures, but maintaining it stably has proven difficult. Jupiter, by contrast, holds vast quantities of it naturally, sustained by gravity's steady grip. The deeper we drift in thought, the warmer it becomes. Temperatures rise to thousands of degrees Celsius. The pressure climbs into millions of times that at Earth's surface. And still, there is no clear dividing line, no hard shell separating layers. The transition is gradual, continuous. Above, storms swirl in colorful bands. Far below, metallic hydrogen flows silently, unseen and unfelt by distant observers. The atmosphere and the interior are not separate worlds. They are connected by slow currents of heat rising upward from the depths. This structure, clouds, molecular hydrogen, liquid hydrogen, metallic hydrogen, creates a planet unlike any rocky world. It is fluid, layered, dynamic. It does not have tectonic plates or continents. Instead, its structure is governed by physics under extreme compression. There is something almost soothing about the idea of gradual change under pressure. Hydrogen adapting, rearranging, responding to gravity's insistence. No abrupt fracture, no sharp break, just a steady deepening into new states of matter. And yet, beneath even the metallic hydrogen, questions remain. Does Jupiter possess a solid core at its center? Is there rock and ice compressed into something dense and distinct? Or has that core dissolved partially into the surrounding layers? To answer that, we must descend still further toward the hidden heart of the giant. As we continue our slow descent through Jupiter's immense interior, beyond the vast ocean of metallic hydrogen, we approach a region that remains one of the most intriguing mysteries in planetary science: the core. For many years, scientists imagined Jupiter's core as something relatively straightforward: a dense, compact mixture of rock and ice, perhaps 10 to 15 times the mass of Earth, sitting solidly at the planet's center. This idea fit neatly into models of planetary formation. In those models, a young Jupiter first formed a heavy core of solid material. Once that core became large enough, it gravitationally attracted enormous quantities of surrounding hydrogen and helium gas, rapidly building the giant planet we see today. This core accretion model remains influential, but reality, as it often does, has proven more nuanced. When NASA's spacecraft Juno entered orbit around Jupiter in 2016, it began making extraordinarily precise measurements of the planet's gravitational field. By carefully tracking tiny variations in Juno's motion as it passed over different regions, scientists could infer how mass is distributed inside Jupiter. What they found suggested that the core may not be a sharply defined, compact object after all. Instead, the data points toward something more diffuse, perhaps a diluted or partially dissolved core. Rather than a neat, solid sphere of rock and ice, Jupiter's central region may consist of heavy elements mixed gradually into the surrounding metallic hydrogen. In this scenario, the boundary between core and envelope is blurred, much like the gradual transitions we've already encountered. Imagine stirring a dense mineral mixture into a vast ocean of fluid metal. Over time, the edges soften, the materials intermingle, the once distinct core becomes extended, its heavier elements spread across a larger region. This diluted core could extend across a significant fraction of Jupiter's radius, making the planet's interior more complex than once believed. Temperature at the center of Jupiter is estimated to reach around 50,000 degrees Celsius. Hot enough to melt titanium, far hotter than the surface of many stars' cooler outer layers. Pressure there is almost beyond comprehension, tens of millions of times the pressure at Earth's surface. Under such conditions, familiar distinctions between solid and liquid lose their meaning. Matter behaves in exotic ways, compressed into states rarely encountered elsewhere. It is humbling to consider that at Jupiter's center, materials similar to the rocks beneath our feet exist in forms we can scarcely imagine. Squeezed, heated, perhaps partially dissolved into surrounding layers. And yet, despite this inferno of pressure and heat, Jupiter does not shine like a star. Its central temperature, immense though it is, remains far below the threshold required for sustained hydrogen fusion. Gravity compresses, heat rises, but ignition never occurs. There is something quietly elegant about that balance. Jupiter hovers perpetually near, but never crossing, a fundamental boundary in astrophysics. The possibility of a diluted core also tells a story about Jupiter's past. Some researchers suggest that early in its history, Jupiter may have experienced a colossal collision with another massive protoplanet, an object perhaps 10 times the mass of Earth. Such an impact could have disrupted the original core, dispersing heavy elements outward and creating the extended structure Juno now hints at. If so, Jupiter's interior bears the memory of ancient violence, a reminder that even in the serene stillness we imagine tonight, the early solar system was dynamic and chaotic. But over billions of years, that chaos has settled. The planet has cooled gradually, contracted slowly, and established the layered structure we explore in thought. Heat continues to flow outward from the deep interior, feeding atmospheric motion far above. The core, whether compact or diluted, remains hidden beneath tens of thousands of kilometers of dense, conductive hydrogen. We cannot see it directly. No probe has ever descended to such depths. The pressure would crush any known material long before reaching the center. So we rely on gravity, mathematics, and careful measurement, listening to the subtle ways Jupiter's mass tugs at a passing spacecraft. Earlier, we imagined hydrogen transforming into metallic fluid. Now we picture heavier elements, rock, ice, complex compounds, blended into that metallic sea. The deeper we go, the more boundaries soften. Distinctions fade. Everything merges under gravity's steady insistence. And from this hidden interior, metallic hydrogen churning, diluted core compressed, arises one of Jupiter's most striking external features. A magnetic field so vast and powerful that it shapes space itself around the planet. We will drift outward again now, rising from the depths, carrying with us the image of a core blurred and glowing under unimaginable pressure. And we will begin to sense the invisible force that extends far beyond Jupiter's clouds. As we rise gently from Jupiter's deep interior, leaving behind the blurred core and the vast ocean of metallic hydrogen, we begin to sense something invisible, something that cannot be seen with the eye, yet stretches far beyond the planet itself. It is Jupiter's magnetic field. Earlier, we spoke of metallic hydrogen flowing under immense pressure. Because this fluid conducts electricity so efficiently, and because Jupiter rotates so rapidly, powerful electrical currents are generated deep within. These currents create a magnetic field of staggering strength. At the level of Jupiter's cloud tops, the magnetic field is roughly 20,000 times stronger than Earth's. If Earth's magnetic field is like a protective bubble, gently guiding compass needles and shielding us from solar radiation, Jupiter's is more like a vast, luminous fortress. It extends millions of kilometers into space, forming a region known as the magnetosphere. In fact, Jupiter's magnetosphere is the largest continuous structure in the solar system after the heliosphere, the vast bubble created by the sun's solar wind. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear larger than the full moon in our sky. Imagine that for a moment. An invisible structure, carved not from rock or gas but from magnetic force, stretching outward like an enormous, silent wing. The magnetosphere forms as Jupiter's magnetic field interacts with the solar wind, a steady stream of charged particles flowing outward from the Sun. When these particles encounter Jupiter's magnetic field, they are deflected, trapped, or guided along magnetic lines toward the poles. Within this region, charged particles become ensnared in radiation belts far more intense than those surrounding Earth. These belts are filled with high-energy electrons and ions, moving at tremendous speeds. For spacecraft, this environment presents a serious challenge. Electronics must be shielded carefully to survive prolonged exposure. Yet, from a distance, the magnetosphere remains serene, an invisible guardian cocooning the planet. What makes Jupiter's magnetic field especially fascinating is its scale and asymmetry. Measurements from Juno reveal that the field is not perfectly aligned with the planet's rotation axis, nor is it evenly distributed. Some regions are stronger, others weaker, suggesting complex motion within the metallic hydrogen layer below. In certain areas, the magnetic field appears intensely concentrated, as though deep currents are rising closer to the surface. These variations offer clues about the internal dynamics we cannot observe directly. If we could somehow see magnetic field lines, we would notice them arcing gracefully from one hemisphere to the other, looping outward into space before curving back toward the planet. Along these lines, charged particles travel like beads sliding along invisible wires. And here, Jupiter's rapid rotation once again plays a crucial role. As the planet spins, it drags portions of its magnetosphere along with it. The magnetic field does not remain static. It rotates in rhythm with the giant world beneath it. This motion creates immense electrical currents within the surrounding plasma. In a sense, Jupiter's magnetic field is not merely a feature of the planet. It is an extension of its personality, massive, dynamic, influential. It reaches far beyond the visible cloud tops, shaping space around it in subtle but powerful ways. The magnetosphere also interacts with Jupiter's many moons. Some of these moons orbit within this magnetic environment, contributing material to it. One moon in particular, though we will explore it more fully later, continuously releases charged particles into Jupiter's magnetic embrace. All of this unfolds quietly, invisibly, beyond human senses. No sound carries through space. No color marks the boundary. Yet the magnetic influence is real, measurable, and immense. If we pause here and imagine Jupiter suspended in darkness, we might picture not only its striped clouds and swirling storms, but also an enormous, transparent field enveloping it, protective and powerful, extending millions of kilometers into the void. And along the magnetic field lines near Jupiter's poles, something luminous occurs, a phenomenon both beautiful and persistent. Curtains of light, shimmering not briefly as on Earth, but continuously. We have reached the threshold of another quiet wonder, Jupiter's eternal auroras. If we follow Jupiter's magnetic field lines as they arc gracefully toward the poles, we arrive at a spectacle of quiet brilliance, its auroras. On Earth, auroras appear as delicate curtains of green and crimson light, flickering softly near the polar skies. They come and go, responding to bursts of solar activity. Some nights they shimmer brightly. Other nights the sky remains still and dark. On Jupiter, auroras do not wait for special occasions. They are constant, because Jupiter's magnetic field is so powerful, and because its magnetosphere traps enormous quantities of charged particles, energy is continuously funneled toward the planet's polar regions. There, these particles collide with atoms and molecules in the upper atmosphere, primarily hydrogen, causing them to glow. But Jupiter's auroras are not merely scaled-up versions of Earth's. They are fundamentally more intense. Observations show that Jupiter's auroral emissions can shine in ultraviolet and even X-ray wavelengths. In fact, its auroras are the most powerful in the solar system. From above, they form glowing ovals encircling each pole, steady, luminous rings that rarely fade. If we could hover high above Jupiter's North Pole, we would see a radiant halo surrounding the dark center of the polar region. The glow would not flicker gently as on Earth. It would pulse with immense energy, fed continuously by magnetic forces. There is a reason for this persistence. While the sun's solar wind contributes to Jupiter's auroras, a significant portion of the energy comes from within the Jovian system itself. One of Jupiter's moons, Io, plays a particularly important role. Io is volcanically active, constantly releasing sulfur dioxide gas into space. This material becomes ionized, its atoms stripped of electrons, and forms a torus, or donut-shaped ring of plasma, around Jupiter along Io's orbit. These charged particles are captured by Jupiter's magnetic field and accelerated along magnetic field lines toward the poles. As they plunge into the atmosphere at tremendous speeds, they deposit energy, causing hydrogen atoms to emit light. In this way, Io helps power Jupiter's auroras from within, like a generator feeding electricity into a vast luminous display. The result is a magnetosphere-moon interaction unlike anything seen elsewhere in the solar system. Space telescopes and spacecraft instruments have detected bright spots within Jupiter's auroral ovals corresponding to the magnetic footprints of certain moons. These footprints mark where magnetic field lines connecting Jupiter and its moons intersect the atmosphere. It is as though invisible threads tie these worlds together, channeling energy between them. There is something deeply poetic about this connection. A distant moon, orbiting silently, contributes to a glowing crown of light thousands of kilometers away. Motion and magnetism intertwine. Jupiter's rapid rotation also intensifies the process. As the planet spins, it drags plasma within its magnetosphere around with it, creating enormous electrical currents. These currents amplify auroral emissions, ensuring they remain active even when solar activity is low. Unlike Earth's auroras, which are shaped strongly by variations in the solar wind, Jupiter's auroras are largely self-sustaining. They are powered by the planet's own internal rotation and the material supplied by its moons. When viewed in ultraviolet light, the auroras form structured patterns, bright arcs, pulsating spots, and shifting filaments. In X-rays, they sometimes flash with periodic bursts, almost like a heartbeat in space. And yet, despite their intensity, they remain silent. There is no crackle, no whisper of wind, only light flowing gently over the poles of a giant world. If we imagine Jupiter now, its cloud bands encircling its middle, its great red spot turning steadily, its magnetosphere stretching outward, we can also envision glowing halos at each pole, permanent and serene. Earlier, we explored storms within the atmosphere and currents within metallic hydrogen. Now we see how those internal motions ripple outward, shaping light itself. But Jupiter's polar regions hold more than auroras. Beneath the luminous glow, high above the deeper atmosphere, enormous cyclones spin in geometric patterns, vast storms arranged with surprising symmetry. Let us drift closer, toward the poles once more, and examine the intricate choreography of these polar cyclones and the ammonia storms that roam the broader atmosphere. As we drift gently downward from the glowing auroras at Jupiter's poles, we begin to see the atmosphere beneath them, not as a smooth blanket of clouds, but as a realm of immense, organized motion. At lower latitudes, we have already noticed the familiar bands, alternating belts and zones stretching around the planet's circumference. Within these regions, ammonia clouds rise and sink, forming storms that appear as bright plumes or darker patches. Some storms emerge suddenly, bloom for weeks, then fade back into the surrounding haze. Others linger longer, merging or stretching under the influence of powerful jet streams. Ammonia plays a central role in Jupiter's visible weather. In the upper atmosphere, temperatures are cold enough for ammonia vapor to condense into ice crystals. These crystals reflect sunlight efficiently, giving the lighter zones their creamy, pale color. Where ammonia clouds are thinner, we glimpse deeper layers tinted by other compounds, creating the darker belts. Occasionally, towering ammonia storms erupt upward from below, punching through the upper cloud deck. These convective storms are driven by heat rising from Jupiter's interior. Warm material ascends, cools, and spreads outward, creating bright, billowing cloud tops that can span thousands of kilometers. But as we move toward the poles, the atmospheric patterns shift dramatically. Unlike Earth, whose polar regions are relatively calm compared to its mid-latitude storm systems, Jupiter's poles are crowned with enormous cyclones arranged in surprisingly stable geometric formations. Data from Juno revealed that Jupiter's North Pole hosts a central cyclone surrounded by 8 others arranged in a near-perfect octagon. At the South Pole, a central cyclone is encircled by 5 others, forming a pentagonal pattern. Each of these cyclones is immense, thousands of kilometers across, comparable in size to continents on Earth. And yet they remain locked in position relative to one another, like dancers maintaining formation in a slow celestial ballet. On Earth, large cyclones tend to drift, weaken, or collide chaotically. Jupiter's polar cyclones, however, appear remarkably stable. They spin persistently, held in place by a balance of forces, mutual gravitational and atmospheric interactions that keep them from merging into one giant storm. If we could hover above the North Pole, we would see a dark central vortex, surrounded by 8 swirling companions. Their cloud tops curl inward in elegant spirals, each rotating counterclockwise in the northern hemisphere. The symmetry is almost hypnotic. These polar cyclones are not shallow features. Measurements suggest they extend deep into the atmosphere, possibly hundreds of kilometers below the visible cloud tops. They are anchored within Jupiter's layered structure, shaped by the planet's rapid rotation and internal heat flow. And yet, despite their size and power, they move with a kind of measured grace. There is no frantic motion. The rotation is steady, deliberate, as though guided by invisible rails. Meanwhile, across the broader atmosphere, ammonia storms continue their quiet cycles. In some regions, ammonia-rich air rises, condenses, and forms bright plumes. In others, drier air descends, revealing deeper, darker layers. The interplay of rising and sinking gases creates subtle color variations: creams, ochres, muted reds. The jet streams we discussed earlier act as boundaries, confining these weather systems to narrow latitudinal bands. Where opposing winds meet, turbulence forms elongated ovals and swirling eddies. Over time, some of these eddies merge, forming larger storms, occasionally even feeding into features like the Great Red Spot. What makes Jupiter's atmospheric system so mesmerizing is its layered complexity. Heat from the interior rises slowly. Rotation organizes motion into bands. Magnetic influences shape charged particles above. And at the poles, cyclones arrange themselves into stable, almost mathematical patterns. There is a rhythm here, a repetition of rising and sinking, spinning and stabilizing. Storms form, storms dissipate, yet the overall structure persists. If we pause and imagine Jupiter from afar, we might picture its atmosphere as a living tapestry. Bands woven horizontally, cyclones stitched at the poles, plumes of ammonia rising like breath from beneath. Earlier, we traced magnetic lines into glowing auroras. Now we see the storms beneath them, massive yet composed, dynamic yet ordered. And surrounding all of this atmospheric complexity, orbiting silently at varying distances, is a vast family of moons, small and large, icy and volcanic, each contributing in subtle ways to the Jovian system. Let us widen our view now, drifting outward from the poles and storms, to consider the many companions that circle this giant world. As we pull back from Jupiter's swirling poles and layered clouds, the giant planet no longer fills our entire field of view. Instead, we begin to notice faint points of light moving slowly around it, companions tracing patient paths through space. Jupiter is not alone. It presides over a vast and intricate family of moons. For many years, astronomers counted 79 confirmed moons orbiting Jupiter. But observations have continued, and as of 2023, that number has risen to 95 confirmed natural satellites. It is possible that even more small, distant moons remain to be catalogued, tiny fragments captured by Jupiter's gravity, too faint to detect easily. This makes Jupiter the planet with the most known moons in our solar system. These moons are not uniform. They vary dramatically in size, composition, and origin. Some are massive spherical worlds comparable to small planets. Others are irregular, potato-shaped bodies only a few kilometers across. Together, they form a miniature system, almost like a solar system in small scale, with Jupiter at the center instead of the Sun. The moons can be broadly divided into two categories: regular and irregular satellites. The regular moons orbit relatively close to Jupiter and follow nearly circular, orderly paths along the planet's equatorial plane. They likely formed from the same rotating disk of gas and dust that surrounded Jupiter during its early formation, much as planets formed from the disk around the young Sun. The irregular moons, by contrast, are distant and often follow tilted, elongated, or even retrograde orbits, meaning they travel opposite to Jupiter's rotation. These moons were likely captured objects, once wandering independently through the outer solar system before being snared by Jupiter's immense gravity. Imagine small icy bodies drifting through space billions of years ago. As they passed near the growing giant planet, gravitational interactions altered their paths. Some were flung away, others lost enough energy to become bound, trapped in orbit permanently. Over time, collisions may have fragmented some of these captured objects, creating clusters of related moons traveling along similar paths. The result is a complex gravitational dance, dozens upon dozens of bodies circling in layered orbits. Closest to Jupiter are the small inner moons, orbiting within the faint ring system we will explore later. These tiny satellites contribute dust to the rings through micrometeorite impacts. Their gravitational presence helps maintain subtle structures within the ring material. Farther out orbit the large regular moons, worlds so substantial they would be considered planets if they orbited the Sun directly. 4 of these moons are particularly remarkable, and we will devote careful attention to them soon. Beyond them stretch families of irregular satellites grouped by similar orbital characteristics. Some clusters may be remnants of single-parent bodies shattered long ago. The gravitational influence of Jupiter dominates this entire system. Its mass, 318 times that of Earth, creates a deep gravitational well. Any object venturing too close feels its pull. Once captured, escaping requires enormous energy. If we imagine hovering far above Jupiter, we would see not a solitary planet, but a dynamic, layered system of orbits. Inner moons circling swiftly, outer moons drifting slowly across vast distances. The geometry is intricate yet stable, refined over billions of years. It is fascinating to consider that when early astronomers first observed Jupiter through telescopes in the early 17th century, they saw only 4 moons. Those 4 were enough to challenge humanity's long-held assumption that everything revolved around Earth. With improved instruments, the count steadily grew. Each new discovery added nuance to our understanding. Jupiter's gravitational realm expanded in the imagination, and still new moons continue to be found. With sensitive detectors and careful tracking, astronomers identify faint moving points among the background stars, tiny satellites that had gone unnoticed. There is something gently humbling about that. Even now, in our era of advanced technology, the Jovian system continues to reveal surprises. As we drift among these moons in thought, we begin to notice that 4 of them stand out, larger, brighter, and more complex than the rest. They are often referred to collectively as the Galilean moons, after the astronomer who first documented them in 1610. Each of these 4 worlds is distinct. One is the largest moon in the entire solar system. One is a volcanic inferno. One hides an ocean beneath ice. And one is heavily cratered and ancient. Let us move closer now, focusing our attention on this remarkable quartet that transformed our understanding of the cosmos. As we drift closer to Jupiter's inner family of moons, 4 worlds begin to shine with quiet distinction. They are larger than the others, round and luminous, moving in orderly paths close to the planet's equatorial plane. These are the Galilean moons, named after the Italian astronomer Galileo Galilei, who first observed them through a telescope in 1610. When Galileo turned his modest instrument toward Jupiter, he noticed 3 small points of light aligned beside the planet. On subsequent nights, their positions changed. Soon he realized there were 4 of them, and that they orbited Jupiter itself. This discovery was profound. It demonstrated that not everything revolved around Earth. Another center of motion existed in the heavens. Those 4 moons are now known as Ganymede, Io, Europa, and Callisto. Each one is a world unto itself. Ganymede is the largest moon in the entire solar system. It is even larger than the planet Mercury. If it orbited the Sun independently, we might easily classify it as a small planet. Its surface is a mix of bright grooved terrain and darker, heavily cratered regions. Beneath its icy crust lies a differentiated interior, layers separated by density, and remarkably, it possesses its own intrinsic magnetic field. It is the only known moon with such a feature. Io, by contrast, is a world of fire. It is the most volcanically active body in the solar system. Its surface is mottled with yellows, oranges, and reds, colors created by sulfur compounds ejected from hundreds of volcanoes. Tidal forces from Jupiter knead Io's interior continuously, generating heat through friction. The result is constant eruption. Lava fountains arching high above the surface, reshaping the landscape again and again. Europa appears serene at first glance. Its surface is smooth and bright, crisscrossed by dark linear fractures. Beneath its icy shell, strong evidence suggests the presence of a global subsurface ocean of salty liquid water. Tidal interactions with Jupiter provide enough internal heat to keep this ocean from freezing solid. Among all known worlds beyond Earth, Europa stands as one of the most promising places to search for extraterrestrial life. Callisto, the outermost of the four, tells a quieter story. Its surface is heavily cratered, preserving scars from billions of years of impacts. Unlike Io and Europa, it shows little sign of recent geological activity. It appears ancient, stable, and deeply marked by time. Beneath its surface, there may also be a subsurface ocean, though less certain than Europa's. Together, these four moons form a miniature system governed by resonance. Io completes 4 orbits around Jupiter in the time it takes Europa to complete 2, and Ganymede to complete 1. This orbital resonance locks their gravitational interactions into a rhythmic pattern. Each time they align in certain configurations, tidal forces flex their interiors, generating heat, especially within Io and Europa. It is a delicate gravitational dance, repeating over and over across eons. If we imagine hovering far above Jupiter now, we might see these 4 moons tracing luminous arcs around the giant planet. Io closest, moving swiftly, Europa just beyond, Ganymede farther still, Callisto at the outer edge of the quartet. Each reflects sunlight softly. Each carries a different story of geology, chemistry, and internal heat. When Galileo first observed them, he could not have imagined their complexity. Through his telescope, they were mere points of light. Yet those points shifted nightly, offering a quiet but undeniable revelation. Earth was not the center of all motion. There is something peaceful about that realization. The cosmos is not arranged around us. It unfolds in layers of motion and interaction, independent and vast. Earlier, we explored Jupiter's storms and magnetic field. Now we see how its gravity shapes not just distant asteroids, but entire worlds in close orbit. These moons feel Jupiter's pull intimately. Their interiors are flexed by tidal forces. Their surfaces are sculpted by radiation and gravitational resonance. And among them, Ganymede stands apart, not only for its size, but for its hidden magnetic heart. Let us move closer to that immense moon next, drifting gently toward the largest satellite in the solar system. As we leave Jupiter's immediate cloud tops behind and drift outward through its inner orbital space, one moon grows steadily larger in our view, calm, luminous, immense. Ganymede, Ganymede is not merely the largest moon orbiting Jupiter. It is the largest moon in the entire solar system, with a diameter of about 5,268 kilometers. It surpasses even the planet Mercury in size. If Ganymede orbited the Sun directly instead of Jupiter, we would almost certainly classify it as a planet. And yet here it is, circling a giant world, bound in steady rhythm. Its surface is a patchwork of contrasts. Dark, heavily cratered regions speak of ancient times, terrains that have remained largely unchanged for billions of years. Interwoven among them are lighter, grooved regions, vast swaths of terrain marked by long ridges and furrows stretching for thousands of kilometers. These grooves are thought to have formed through tectonic-like processes long ago. As Ganymede's interior cooled and shifted, its icy crust may have cracked and spread, allowing fresher material to rise and reshape the surface. Unlike Earth's plate tectonics, this movement was not driven by molten rock, but by shifting ice. Beneath that frozen exterior lies a layered interior. Scientists believe Ganymede is differentiated, meaning its materials have separated by density. A metallic core likely rests at its center, surrounded by a rocky mantle, above which lies a thick shell of water ice. Most remarkable of all, Ganymede possesses its own intrinsic magnetic field. This discovery surprised scientists when it was confirmed by spacecraft measurements. Among all known moons, Ganymede is unique in this respect. Its metallic core must be partially molten and convecting, generating a dynamo effect similar in principle to Earth's. The result is a magnetic field embedded within Jupiter's vastly larger magnetosphere. If we could see magnetic field lines, we would notice Ganymede carving out a small magnetic cavity inside Jupiter's enormous magnetic environment, a magnetosphere within a magnetosphere. It is a subtle but elegant phenomenon, a quiet reminder that even moons can carry complex internal lives. There is also compelling evidence that beneath Ganymede's icy crust lies a subsurface ocean. Data suggests that multiple layers of ice and liquid water may exist, stacked like a layered cake deep below the surface. These oceans are kept liquid not by sunlight, but by internal heat, residual warmth, and possibly tidal flexing from gravitational interactions with Jupiter. If so, Ganymede joins a small but fascinating group of icy worlds that may harbor hidden oceans far from the sun's warmth. Standing, if standing were possible, on Ganymede's surface would be an experience of profound stillness. Jupiter would loom enormous in the sky, its striped face filling a vast portion of the horizon. The sun would appear small and distant. The ground beneath would be hard ice mixed with darker rocky material. Craters would stretch across the landscape like silent bowls carved by ancient impacts. Gravity there is gentle, about 1/7 that of Earth's. A slow step would carry you lightly across the frozen plain. Despite its size and complexity, Ganymede feels restrained. There are no towering volcanic plumes as on Io, no vast visible fractures hinting immediately at subsurface oceans like Europa's prominent lineae. Instead, it presents a quieter face, ancient, grooved, subtly magnetic. Earlier, we spoke of Jupiter's immense magnetic field, generated by metallic hydrogen deep within. Now we see that even one of its moons carries a smaller echo of that phenomenon, a metallic core turning slowly, sustaining a magnetic identity of its own. It is fascinating to consider that within the gravitational domain of Jupiter, a planet so dominant and powerful, exists a moon large enough to be a world in its own right, layered and magnetic, ancient yet internally complex. And yet, among the Galilean moons, Ganymede may not be the most dramatic. Closer to Jupiter, another moon endures relentless tidal heating, its surface reshaped continuously by fire, a world painted in sulfur yellows and molten reds. Let us drift inward now, toward that restless volcanic landscape. As we move inward from the calm, grooved expanses of Ganymede, the environment changes dramatically. Jupiter looms larger in the sky, its gravity felt more intensely. And ahead of us, glowing faintly in hues of gold, orange, and deep crimson, is a world that rarely rests. Io is unlike any other moon in the solar system. At first glance, its surface appears almost painted, swirls of yellow sulfur, dark lava plains, patches of red and white frost. But these colors are not static decoration. They are evidence of relentless geological activity. Io is the most volcanically active body known. The reason lies not in its size alone, but in its position. Io orbits very close to Jupiter, so close that the planet's immense gravity constantly tugs at it. But Io does not travel in a perfect circle. Its orbit is slightly elliptical, maintained by gravitational resonances with Europa and Ganymede. As Io moves closer to and farther from Jupiter during each orbit, the strength of the gravitational pull changes subtly. This variation flexes Io's interior. Imagine gently squeezing a rubber ball over and over again. Friction builds inside. Heat accumulates. Now scale that up to a moon hundreds of thousands of times more massive. Jupiter's gravity stretches Io by as much as 100 meters during each orbit. The constant flexing generates enormous internal heat through tidal friction. That heat has nowhere to go but upward. As a result, Io's surface is punctuated by hundreds of volcanoes. Some erupt continuously, others awaken unpredictably, reshaping the landscape in weeks or months. Lava lakes glow faintly in infrared images. Plumes of sulfur dioxide rise hundreds of kilometers above the surface before falling back like gentle, toxic snow. Some eruptions on Io are so powerful that they would dwarf any volcanic event in recorded human history. Lava fountains arc high, spreading molten rock across plains already reshaped countless times before. Unlike Earth, Io does not display stable tectonic plates or long-lived mountain chains. The surface is constantly renewed. Craters from impacts are rare, erased by fresh lava flows and deposits. The moon's crust is in a perpetual state of transformation. And yet, despite its violence, there is a strange rhythm to Io's existence. Each orbit takes about 1.77 Earth days. With every revolution, the gravitational kneading continues. Stretch, relax, stretch, relax. The process is steady, predictable, woven into the orbital dance established billions of years ago. Io's thin atmosphere, composed primarily of sulfur dioxide, collapses and reforms as it moves in and out of Jupiter's shadow. When illuminated by sunlight, frost sublimates into gas. When in darkness, it freezes again onto the surface. Even its atmosphere participates in the cycle. Earlier, we spoke of Jupiter's auroras being powered in part by material from Io. Here is where that story deepens. As volcanoes eject sulfur and oxygen atoms into space, some of these particles escape Io's weak gravity and become ionized by sunlight. They form a torus, a donut-shaped ring of plasma along Io's orbit. Jupiter's magnetic field captures this plasma and accelerates it, contributing energy to the giant planet's auroral displays. So Io does not merely endure Jupiter's influence, it contributes to Jupiter's brilliance. If we could stand on Io's surface, carefully shielded from radiation, we would see Jupiter dominating the sky, enormous and striped. The ground beneath might tremble faintly from distant eruptions. The horizon would glow with sulfurous haze. Gravity would be light, about 1/6 that of Earth, allowing long, slow leaps across volcanic plains. There is something deeply interconnected about this system. Jupiter's gravity heats Io. Io's eruptions feed Jupiter's magnetosphere. Magnetic currents return energy to Jupiter's poles in luminous arcs. Motion creates heat. Heat creates change. Change feeds light. Among the Galilean moons, Io is the most restless, the most visibly alive in geological terms. And yet, just beyond it, another moon presents a quieter, more enigmatic face. Smooth, pale, etched with dark lines like cracks in frozen glass. Let us drift outward slightly now, toward that icy world whose secrets may run deeper than we can see. As we move outward from the fiery restlessness of Io, the landscape softens. The colors shift from sulfur yellows and molten reds to pale whites and faint browns. Before us now is a world that appears calm, almost serene at first glance. Europa. Europa's surface is one of the smoothest in the solar system. It reflects sunlight brightly, giving it a luminous, almost pearlescent glow against the dark backdrop of space. Unlike heavily cratered moons such as Callisto, Europa shows relatively few large impact scars. The surface is young, constantly renewed. But what truly defines Europa is not what lies on top. It is what may lie beneath. Stretching across its icy crust are long, dark streaks called lineae. These fractures crisscross the surface in intricate patterns, some extending for thousands of kilometers. They resemble cracks in sea ice on Earth, frozen mid-shift. The lines are thought to form as Europa's icy shell flexes under tidal forces from Jupiter. Just as Io is kneaded by Jupiter's gravity, Europa too experiences tidal flexing, but to a lesser, more measured degree. This flexing generates internal heat, not enough to melt the entire moon, but sufficient to keep a subsurface ocean in liquid form beneath the frozen crust. Beneath Europa's outer ice shell, perhaps 10 to 30 kilometers thick, scientists believe there exists a global ocean of salty liquid water. That ocean may be 100 kilometers deep, containing more water than all of Earth's oceans combined. The thought alone is profound. An ocean in darkness, warmed not by sunlight but by gravitational energy. Tides rising and falling beneath ice, driven by Jupiter's pull. Currents moving slowly in blackness, insulated from the vacuum of space above. Evidence for this hidden ocean comes from multiple lines of observation. Magnetic measurements suggest that Europa conducts electricity in a way consistent with a salty liquid layer beneath its surface. Surface features resemble ice rafts that have broken apart and refrozen, similar to pack ice on polar seas. There are also regions where the ice appears to have risen and collapsed, hinting at material moving upward from below. Some scientists even suspect that water vapor plumes occasionally erupt from Europa's surface, faint geysers venting ocean material into space. While still under investigation, Such plumes would provide a tantalizing opportunity to sample subsurface chemistry without drilling through kilometers of ice. If we imagine standing on Europa's surface, the experience would be stark and quiet. The ground beneath would be solid ice, tinted faintly by salts and radiation. The sun would appear small and distant. Jupiter, enormous in the sky, would hang as a constant presence, its gravity subtly flexing the world beneath your feet. Gravity on Europa is gentle, about 1/8 that of Earth's. A careful step would feel light and slow. But beneath that frozen plain, tidal forces are at work. The ice shell may rise and fall by several meters during each orbit, flexing rhythmically. That motion generates heat through friction, maintaining the hidden ocean. Why does this matter so much? Because where there is liquid water, energy, and chemistry, there is potential for life. Europa's ocean is shielded from harsh radiation by its ice crust. Hydrothermal vents may exist at the ocean floor, driven by internal heat. On Earth, such vents teem with life, independent of sunlight. If similar processes occur on Europa, microbial ecosystems could exist in total darkness. We do not yet know, but future missions aim to study Europa more closely, mapping its surface in greater detail and searching for chemical signatures that might hint at habitability. Earlier, we explored storms, magnetic fields, volcanic fire. Now we consider water, silent, hidden, vast. In Jupiter's domain, diversity thrives. One moon burns, one freezes, one holds ancient scars, one hides an ocean, and still beyond these three, Io, Europa, Ganymede, there remains the outermost of the quartet. A world marked deeply by time, carrying the memory of countless impacts. Let us drift slightly farther outward now, toward that ancient and cratered landscape. As we move beyond Europa's pale, fractured surface and drift farther outward, the glow of Jupiter softens slightly in the sky. The gravitational pull remains strong, but the environment feels quieter, more distant from the intense tidal flexing that shapes the inner moons. Before us stretches a darker, heavily marked world, ancient and patient. Callisto. Callisto is the outermost of the 4 Galilean moons, orbiting Jupiter at a comfortable distance compared to Io, Europa, and Ganymede. Because it lies farther away, it does not experience the same intense tidal heating. Its interior has remained relatively undisturbed for billions of years. The surface of Callisto is one of the most heavily cratered landscapes in the solar system. Impact craters overlap and layer upon one another, forming a tapestry of scars that record the history of early solar bombardment. There are enormous multi-ring basins, vast circular structures formed when massive objects collided with the moon long ago. One such basin spans thousands of kilometers, its rings spreading outward like ripples frozen in stone. Unlike Io, whose surface is constantly reshaped by volcanic eruptions, or Europa, whose ice crust shifts and fractures, Callisto preserves its past. It is geologically quiet. There is little evidence of active tectonics. No towering plumes, no resurfacing lava plains. Instead, Callisto's terrain appears stable, cold, and ancient. And yet, beneath that ancient exterior, there may still be complexity. Magnetic measurements suggest that Callisto could harbor a subsurface ocean of salty liquid water buried deep beneath its icy crust. Unlike Europa's ocean, which is kept warm by strong tidal heating, Callisto's possible ocean may be sustained by a combination of residual heat and insulating layers of ice. If so, even this quiet, cratered world may conceal hidden layers of liquid beneath its frozen shell. Imagine standing on Callisto's surface. The sky would be dark except for the distant sun and the looming presence of Jupiter. Smaller than seen from Io or Europa, but still commanding. The ground beneath would be a mixture of ice and rock, broken by craters of all sizes. Gravity there is gentle, about 1/8 of Earth's, similar to Europa. A step would carry you lightly across terrain shaped by impacts rather than by fire or shifting ice. Callisto's distance from Jupiter also means it lies partially outside the most intense regions of the giant planet's radiation belts. This relative stability has made it a candidate in discussions of potential future human exploration in the Jovian system. Of all the Galilean moons, Callisto presents the least severe radiation environment. Earlier, we explored Ganymede's magnetic field, Io's volcanic fury, Europa's hidden ocean. Now we see Callisto's story, a record of time etched in craters, a moon shaped more by external impacts than by internal heat. Together, these four moons form a gradient of activity. Closest to Jupiter, Io burns with volcanic energy. Slightly farther, Europa flexes and hides water beneath ice. Ganymede carries its own magnetic identity. And farthest out, Callisto rests in ancient stillness. But Jupiter's influence extends beyond its immediate family of moons. If we widen our view even further, beyond Callisto's orbit, we encounter a vast region of space shaped subtly yet profoundly by Jupiter's gravity, the asteroid belt. Between Mars and Jupiter lies a broad ring of rocky debris, fragments that never coalesced into a planet. And Jupiter's presence is central to that story. Let us turn our attention now to this silent sculptor of the solar system, the giant whose gravity prevented a world from forming. As we drift outward beyond the orbit of Callisto, leaving Jupiter's immediate family of moons behind, the space between worlds grows wider and quieter. Yet Jupiter's influence does not end there. Its gravity extends far into the solar system, shaping regions that at first glance might seem distant and unrelated. Between the orbits of Mars and Jupiter lies the asteroid belt, a broad ring of rocky and metallic fragments encircling the Sun. These objects vary in size from tiny dust grains to dwarf planet-scale bodies like Ceres. Long ago, during the formation of the solar system, this region contained enough material that a planet might have formed there. But it did not. Jupiter's immense gravitational presence prevented that possibility. As rocky bodies in the early asteroid belt began to clump together, Jupiter's gravity tugged at them. Its influence introduced orbital resonances, mathematical relationships between orbital periods that amplified gravitational effects. In certain regions, objects orbiting the Sun would complete, for example, 3 revolutions for every one of Jupiter's. These repeating alignments created subtle but persistent gravitational nudges. Over time, these nudges destabilized orbits. Instead of gradually merging into a single planet, many asteroid fragments were stirred, scattered, or prevented from coalescing. Some were ejected inward toward the Sun. Others were flung outward. The result was fragmentation rather than formation. These resonance gaps within the asteroid belt are known as Kirkwood gaps, regions where few asteroids are found because Jupiter's gravitational rhythm disrupts stable orbits there. So while Jupiter acts as a protective guardian by deflecting comets and absorbing impacts, it also played the role of cosmic architect, shaping the distribution of material in the early solar system. This gravity is both stabilizing and disruptive, depending on perspective. And sometimes that protective role becomes dramatically visible. In July of 1994, a fragmented comet known as Comet Shoemaker-Levy 9 collided with Jupiter. This comet had been captured by Jupiter's gravity earlier. During a close approach in 1992, tidal forces from the giant planet stretched and tore the comet apart into more than 20 distinct fragments. These fragments continued orbiting Jupiter for 2 years before returning on a collision course. Over the course of several days in July 1994, each fragment plunged into Jupiter's atmosphere at tremendous speed. The impacts released energy equivalent to millions of megatons of TNT. Dark scars appeared in Jupiter's cloud tops, bruises visible even through amateur telescopes on Earth. Some of these impact marks were larger than Earth itself. For months, those dark patches lingered in the atmosphere before gradually dissipating. It was the first time humanity had directly observed two solar system bodies colliding in real time, and it served as a vivid reminder of Jupiter's role as both attractor and shield. Had such a comet ventured inward toward Earth instead, the consequences could have been catastrophic. Instead, Jupiter absorbed the blow. There is something sobering yet reassuring about that image. A giant world quietly enduring impacts that might otherwise threaten smaller planets. Jupiter does not actively protect Earth in a conscious sense, of course. It simply obeys gravity, but its mass creates a gravitational buffer in the outer solar system, influencing the paths of countless objects. Even today, Jupiter continues to capture and redirect comets. Some become temporary moons before escaping again. Others are consumed. As we imagine Jupiter suspended in darkness now, we might picture faint trails of icy bodies approaching from the distant outer reaches, nudged by subtle gravitational shifts. Some will pass safely by. Some will be deflected. A few may end in fiery descent through the giant planet's atmosphere. Earlier, we explored storms, moons, magnetic fields. Now we see Jupiter's broader influence, extending across millions of kilometers, shaping not only its immediate surroundings, but entire regions of the solar system. And yet, beyond its moons and gravitational dominion, Jupiter carries another subtle feature, one far less prominent than Saturn's, yet present nonetheless. A ring system, faint and delicate, encircles the giant planet. Let us drift inward again, toward those subtle rings of dust and light. As we glide back inward toward Jupiter, leaving behind the wide expanse of the asteroid belt and the memory of cometary impacts, something delicate begins to emerge against the darkness. It is not as luminous as Saturn's grand rings. It does not blaze with icy brilliance. Instead, it is faint, almost whisper-thin, a subtle halo of dust encircling the giant planet. Jupiter has a ring system. These rings were discovered in 1979 by the spacecraft Voyager 1 as it passed through the Jovian system. Unlike Saturn's wide, bright rings composed largely of reflective ice particles, Jupiter's rings are made primarily of fine dust, dark, tenuous, and difficult to see except under specific lighting conditions. If we imagine hovering near Jupiter's equatorial plane and looking sideways toward the planet, the rings would appear as a thin, diffuse band extending outward from the cloud tops. They are subtle, almost ghost-like. The main ring is relatively narrow, extending only a few thousand kilometers in thickness. Beyond it lie fainter structures known as gossamer rings, so named because of their delicate, translucent appearance. Where does this dust come from? The source lies in Jupiter's small inner moons, tiny, irregularly shaped bodies orbiting close to the planet. Micrometeorites constantly strike these moons, knocking small particles of dust into space. Because the moon's gravity is weak, much of this debris escapes into orbit around Jupiter. Over time, these dust grains form the ring system. Radiation pressure, electromagnetic forces, and gravitational interactions shape their distribution, creating faint but persistent structures. Unlike Saturn's rings, which are composed of chunks of ice ranging from small pebbles to house-sized blocks, Jupiter's rings are dominated by microscopic particles. They scatter sunlight weakly, making them difficult to detect from Earth without specialized instruments. And yet, they are there, a reminder that even the largest planet carries delicate features. The rings are not static. Dust is continuously replenished by ongoing impacts on the inner moons. At the same time, particles are gradually lost, spiraling inward toward Jupiter under the influence of electromagnetic forces and gravity. The system is dynamic but subtle, maintained in a quiet balance. If we could float within Jupiter's ring plane, the view would be extraordinary. The planet's immense striped globe would dominate one side of the sky. Tiny dust grains would drift silently past, catching faint sunlight. Beyond them, the stars would shine steadily in the blackness. There would be no sound, only motion, slow, persistent, gentle. Earlier, we considered Jupiter's magnetic field extending millions of kilometers into space. That magnetic environment interacts with ring particles as well. Charged dust grains respond to magnetic forces, altering their trajectories slightly. Even here, invisible currents shape visible structures. The contrast between Jupiter's massive presence and its delicate rings is striking. A planet capable of absorbing comet impacts larger than Earth, yet encircled by a fragile veil of dust. Nature often balances extremes in this way, power and subtlety existing side by side. As we drift slightly above the rings and look back at Jupiter as a whole, we see a world of layers. Deep metallic hydrogen generating magnetic fields, diluted core under immense pressure, storms swirling in bands, auroras glowing at the poles, moons orbiting in complex resonance, faint rings whispering around the equator. And beneath it all, something else continues. An invisible process unfolding slowly over billions of years. Jupiter radiates more energy than it receives from the sun. Its interior is still contracting, ever so slightly releasing heat in the process. Let us move now toward this final quiet aspect of the giant planet. Its slow cooling, its gradual gravitational contraction, its steady emission of internal warmth into space. As we settle into this final movement of our journey, let us step back, far enough that Jupiter becomes whole again in our view. Its faint rings form a subtle line across its equator. Its cloud bands wrap gently around its immense body. The great red spot turns steadily in the southern hemisphere. Auroras shimmer at the poles. Moons trace quiet arcs in layered orbits. And beneath all of it, something patient and nearly imperceptible continues. Jupiter radiates about 2.5 times more energy than it receives from the Sun. At first, that may seem surprising. After all, Jupiter is 5 times farther from the Sun than Earth is. Sunlight there is faint, only about 1/25th as intense as what reaches our planet. And yet, Jupiter emits more heat than it absorbs. The source of this excess energy is not nuclear fusion. Jupiter never ignited as a star. Instead, the explanation lies in a slow and steady process known as Kelvin-Helmholtz contraction. Over billions of years, Jupiter has been gradually shrinking. Not dramatically, not in a way visible to casual observation. The contraction is subtle, only a few centimeters per year, but across immense spans of time, even a few centimeters add up. As Jupiter contracts under its own gravity, gravitational potential energy is converted into heat. That heat flows outward from the interior, rising through layers of metallic hydrogen and molecular hydrogen, eventually reaching the cloud tops and radiating into space. This internal heat helps power Jupiter's atmospheric dynamics. It feeds convection, sustains storms, and contributes to the persistence of features like the Great Red Spot. It also ensures that Jupiter's upper atmosphere is warmer than it would be from sunlight alone. If we imagine Jupiter in infrared light, it would glow softly, not bright like a star, but warmer than the darkness around it. There is something deeply meditative about this slow contraction. A giant world, cooling and compressing over billions of years, not collapsing violently, not flaring into brilliance, just quietly releasing stored energy from its formation. When Jupiter first formed from the swirling disk of gas and dust around the young sun, it was hotter and larger than it is today. Over time, it radiated away much of that initial heat. The planet we see now is the result of gradual settling, a balance between gravity pulling inward and pressure pushing outward. Even today, that balance continues to adjust ever so slightly. Earlier, we spoke of Jupiter as a failed star, but perhaps it is better to think of it as a world that found equilibrium. It gathered enormous mass, enough to dominate its region of space, but not enough to ignite fusion. It became a guardian rather than a sun. This gravity shaped the asteroid belt. Its pull redirected comets. Its magnetic field carved vast structures into the solar wind. Its moons evolved into worlds of fire, ice, and hidden oceans. And yet Jupiter itself remains what it has always been, a gas giant slowly cooling in the dark. If we allow our thoughts to slow now, we can imagine Jupiter turning gently, completing another rotation in under 10 hours. The storms continue. Its auroras glow. Its rings drift softly. Its moons move in patient resonance. Deep inside, metallic hydrogen flows. A diluted core rests under immense pressure. Heat rises slowly upward, escaping into space. There is no urgency in this process. No rush. Only gradual change measured not in human lifetimes, but in geological and cosmic epochs. As we reach the end of our exploration, let us linger for a moment in that stillness. Picture Jupiter suspended against a field of distant stars, vast, layered, quietly radiant. Its presence reminds us that the universe is full of gradients, between planet and star, between fire and ice, between motion and stillness. Jupiter occupies a place along those gradients, steady and immense. And now, as our journey winds down, allow the image to soften. The bands blur gently into one another. The storms slow in your imagination. The auroras dim to a faint glow. The rings fade into darkness. Jupiter continues its slow contraction, the slow rotation, its silent watch over the outer solar system. Wherever you are, let that image rest in your mind for a moment longer, a giant world cooling quietly in the vastness of space.